Hello, in this bonus video, I would like to talk about um, an, an intricacy about the sample standard deviation. And well, let me first just tell you the idea. Expected value of the standard sample standard deviation is not equal to population standard deviation. That's the interesting point. So why is a page related to statistical quality control is open? Actually, this is one of the most interesting applications of that the expected value or the standard deviation, sample standard deviation is actually a biased estimate of population standard deviation, and statistical quality control is one of these areas. I'm not going to go into the details about statistical quality control, but I'm just going to give a general idea. Maybe there's going to be another bonus video later in which later I'm going to talk about statistical quality control in a little bit more detail. So in a nutshell, statistical quality control is actually it's a field of statistical control can be broadly defined as use of statistical and engineering methods in measuring, monitoring, controlling, and improving quality. That's why it's also called quality control. Statistical quality control is a field that dates back to 1920s. Dr. Walter Sheward of Bell Telephone Laboratories was one of the early pioneers of the field. And in 1924, he wrote a memorandum showing a mother control chart, one of the basic tools of statistical process control. So basically, it says that this is about maintaining the quality in a process. And Sheward was one of the pioneers of this field. And he came up with the idea about a control chart. And in also the methods that we use in statistical process control chart is possibly the most important or one of the most important methods or tools that we use. So what is a process control chart? Well, it typically, process control chart is something like this. We have a sample statistic that we would like to monitor. Let's say that is going to be Sbar. It's going to be, we are going to monitor this Sbar and see that in the process, with respect to time, is there a change in this Sbar value with respect to our expected value? So this central line is our expectation of the statistic, and these upper control and lower control values are, as the name suggests, these are the, not that these are not the critical values, but they are upper and lower control levels. Right, these levels are, as long as we stay within those boundaries, then we are going to deem our process to be in control. If we are outside these boundaries, either on the top or on the bottom, then we are going to assume that the process is out of control. I'm not going to go into the details about being in control and out of control. As I said, maybe I'm going to talk about later in another bonus video. But what we do is, for example, if we are producing a drug, a pill, you randomly select, let's say, 5 of these pills from a certain batch. And let's say that the variable that we are interested in is the weight of each of these pills. So we measure each of these 5 pills, we take their averages, and we plot the average value here. Let's say that this is the average value. Well, corresponding to our expected value is pretty much close, and corresponding to lower and upper control limits, it's between those two. And in the next batch, we again take a sample of 5 pills, we weight each of them, and we take an average weight value, and we plot the sample average value here. It is still within the limits. So we draw this chart. There are a couple of more rules related with that. It's not only being upper and lower control limits. There may be some additional rules, but that's the general spirit of the procedure. You determine previously or preliminary, you determine a center line, the expected value of your statistic, and upper and lower control limits. Then during the procedure, you sample the products, you measure the variable that you are interested in, and it's not going to usually consist of, it may, but it's not usually going to consist of a single observation. It's going to consist of probably something like 5 to 9 observations, right? And from those bunch of 5 to 9 observations, you come up with a statistic. This may be X bar. You plot it with respect to time. This is the general idea. All right, now it's not only X bar that we are interested in. We are also interested in, for many cases, the spread of data, because it's X bar only is related to the location of data, right? The sample mean describes the location of our data, location of our process. And as I said earlier, the standard deviation, the width of the data is also, or the width of the process is also very much important. Why? Because to have a good quality product, the variability between products of your products should be small. If you take 5 pills, and if the average value is equal to the presupposed value, to the aim value, that's good, but that's not sufficient. The weight of the pills should also be close to each other. If one of them is 1 gram, the other is 10 gram, that's an awful batch, that's an awful production method, I may say. So it's also the sample variability is important. So the thing that we do is, from those 5 or 9 or whatever the number of pills, but usually it's going to be a small number that we collect, not only we measure X bar, but we also measure sample standard deviation. And the next thing that we do is, just like an X bar chart that we have here, right? For instance, that may be an X bar chart. We have also a sample. So just like we have a sample mean chart, we have also a sample standard deviation chart. And now comes the interesting point. So just like, again, an X bar chart, we are going to have an expected value and upper and lower control limits. The interesting point is this: when you obtain a Sbar value, you divide it by a constant C4 that is tabulated for various sample sizes in any statistics or in any statistical quality control book that you can find. They are in those tables. So actually, I'm going to show this table in a minute also. We divide the sample standard deviation value by some constant. So that's an interesting thing to evaluate, to determine the population standard deviation value. So this actually points that sample standard deviation here. Well, actually, we have bar here. We have the average of these values. That's not that much important why we take the average. It's because of what we call phase 1 sampling. That's too much detail. But the moral of the story is, we divide the sample standard deviation by a term to obtain an unbiased estimate for population standard deviation. And the table here is going to be, if I can find it very fast, let me see, table 8. It's going to be somewhere, say here, because I think it's going to be, the next one is going to be that table. Yes. For instance, if you take a sample of 5 elements, and if you determine the standard deviation of those 5 observations, then you are going to divide the sample standard deviation by 0.94 to obtain an unbiased estimate of population standard deviation, which means expected value of S is not equal to population standard deviation. That's the interesting thing, and that's the point I would like to talk about in this bonus lecture. First of all, let me talk about something very simple. So it's going to be the proof that the expected let me use this colored one. I'm going to prove that expected value of S is not equal to this. Expected value of sample standard deviation is not equal to population standard deviation. Let me edit, although expected value of sample variance is equal to population variance. And that may seem very strange, but it is the case. Actually, there are different ways of proving this. Let me first write it. This is the statement that I suggest, and then I'm going to be talking about that statement. So the first method to talk about this. Actually, it may seem awkward at best sight, but I think it's very easy, because expected value of S square is equal to sigma square. This is something we have proved previously. If you take the square root of both sides, it's going to be expected square value of sample variance in square root is going to be equal to sample standard deviation. Now, if this would be the case, note that we should be able to write this here. So that expected value of S is going to be equal to the square root of expected value of S square, which is going to be equal to sigma square. Unfortunately, this statement, and of course this corresponding statement, is incorrect. Therefore, they are not generally equal to each other. Why? Actually, this square root is a nonlinear operation. And since this is a nonlinear operation, you cannot change the expected value, and this square root operations, you cannot change the location of those two. So therefore, note that it's going to be just square root is out, expected value is in. We make this assumption here for this relation to hold, right? So expected value of S to be equal to sigma. This is simply actually a very simple mathematical indicator that this is not going to be the case. A better proof is going to be like this. Now let's define S to be equal to 1 over n minus 1. I think I was using lowercase letter from n to n, xi minus x bar square in square root. Now what I'm going to do is that this is how a sample standard deviation is defined. If I take the variance of S, it means from sample to sample, how S sample standard deviation would change. This is going to be equal to expected value of, expected value of S square minus expected value of S square. This is just the definition of variance, all right? So, and note that variance should be greater than equal to 0. Right? This is the definition of, actually, this is due to the definition of variance. In this case, expected value of S square is going to be greater than expected square S. That's great. Now, let's continue. Note that S square is the one without the square, square root here. 1 to n xi. This is sample variance. And we know that expected value of sample variance is actually equal to population variance. This is going to be greater than, note that this is going to be again expected value of S square. If you take the square root of both sides, you are going to have expected value of S is going to be smaller equal to the population standard deviation. Now I would like to determine how to find, I would like to determine the expectation of sample variance for a normal random variable. And okay, so the assumption that we previously showed that the variance of the expected value of sample variance is going to be generally smaller than population variance. Therefore, it's going to be a negatively biased estimate of population variance. But can we find the exact value of that bias, or can we find the expected value of sample variance explicitly? Actually, for a normal random variable, this is pretty much easy. For a normal random variable. Because actually for a normal random variable, we know that this quantity is chi-square distributed, n-1, and I'm going to call this k, which is the degrees of freedom, S square over sigma square. This is chi-square distributed with k number of degrees of freedom. And I'm going to show you how to find the expected value of x here. Note that actually this is expected value of x square, the quantity that we are interested in, and this is going to be expected value of x. You may ask, what's that got to do with S square, or actually sample standard deviation? actually this quantity is going to be equal to so using this expression, we are going to find expected value of S. And how are we going to find this expression? Note that this is going to be equal to expected value of S squared. And Sx is going to be equal to expected value of, if you take this term and this side and to this side, is going to be equal to, in square root, is going to be sigma square x square over k. And this is going to be simply equal to sigma square root of k expected value of x. So once we find what expected value of x, which is defined here, while multiplying by population standard deviation and square root of degrees of freedom, we are going to be finding expected value of s. But first, I'm going to show you how to determine expected value of s square using chi-square density, chi-square random variables density function. So I'm going to first find this, then determine this one. Okay, we need actually one additional information in order to, actually two things in order to determine these quantities. The first thing that we need to know is what the so-called gamma function. This function is called gamma function. I'm not going to go into mathematical details about that. It's going to be x to the power alpha minus 1 exponential minus x dx. And here alpha is going to be greater than 0. This function, the right-hand side, is called a gamma function, and you are going to find the gamma function of alpha by giving any values of alpha greater than 0. Now, actually, if you perform this integration, what you end up with will be this relation. So alpha plus 1 is alpha times this quantity. This is going to be actually equal to alpha times alpha minus 1, and it goes like this until gamma function of 1. And this gamma function of 1 is actually equal to 1. Well, if this may actually remind you of some other function that we know. Actually, for discrete or for integer alpha values, gamma function, this function, if I can write it, this gamma function is actually a representation of the factorial. So what we call factorial, actually, we can represent this as using the factorial. So think about the idea like this. This is going to be equal to 1 times gamma function. 3 is going to be equal to 2 times gamma function times 2. And it goes like this. This is going to be equal to 3 times gamma function. And we can easily write by using induction, actually, gamma function of n plus 1 is going to be equal to n factorial. So here, for instance, this is going to be equal to 1, right? This because it was equal to 1 here. And this is going to be equal to 2 factorial. This is going to be equal to 3 times this quantity, which is 3 times 2 factorial, which is 3 factorial. Therefore, this relation holds. So basically, a way of the gamma function is a method of making the discrete factorial function converting to a continuous form, I may say. The mathematical details are not important here, but actually, this is the form, the definition of the gamma function that we are going to be using, the very first thing. And the second thing that we need is, actually, let me write it here, is the distribution, is the probability density function of chi-square distribution. Now, without any proof, chi-square distributed random variable with k degrees of freedom is going to be equal to 1 over, and actually I should copy here in order to not make a mistake. Yes, this is gamma function evaluated at k over 2, and it's going to be x k to the power k over 2 minus 1 exponential minus x over 2. And this is again is going to be valid for x greater equals 0, because the chi-square random variable is a non-negative number, random variable. All right, so using these two, this one and this one, these two properties, what I would like to find is these two quantities. First, let's find this quantity so that we get used to this, how to use this gamma function and the probability density function here. Then we are going to apply this, the experience that we gain here from the actual problem that we are interested in, which is the expected value of the sample standard deviation. Okay, so expected value of s square is going to be simply equal to, note that this is going to be our x square random variable, or let's put it that way, let's write the exact relation. Actually, expected value of s square is going to be equal to expected value of sigma square over k times x square. Therefore, sigma square over k, expected value of x square is going to be, so the quantity that we are searching for is actually equal to this quantity. So we only need to determine this one. Once we determine this quantity, we are going to multiply by these two constants. So the question boils down to what is the expected value of x square random variable. Now, since x square random variable is distributed in this manner, let's remember the definition of expected value. Expected value of, let's say, y is going to be equal to y fy. This is going to be integrated over the domain or support of y. It's going to be from minus infinity to plus infinity. So the general definition of expected value. Now we are going to apply the same expectation formulation here on x square. Expectation of x square here is going to be equal to, one may tend to think that at first sight we are going to write x square here. No, please note that x square is given a new name to it, chi-square random variable. The expectation of the chi-square random variable is going to be equal to, from 0 to plus infinity, is going to be x itself, the random variable itself with this distribution. And the distribution is going to be 1 over 2k to the power 2 gamma function evaluated k over 2 x raised to the power k over 2 minus 1 exponential minus x over 2 dx. And these are the constants. We can take these out of the integral, and x is going to be multiplied by this x raised to this power, and it's going to be x to the power plus 1. So these two are going to be equal to 0. So expectation of x, the chi-square random variable is going to be equal to 1 over 2 to the k to the power 2 gamma function evaluated. K over 2 is going to be from 0 to plus infinity x k over 2 exponential minus x dx. Now note that this form of the function x raised to the power k over 2 and exponential raised to the some function of x is very much like gamma function. So let's make it exactly look like gamma function. So x over 2 is going to be equal to u, x is equal to 2u, and dx is equal to 2 du. So this part, I'm going to only concentrate on this part, including this dx. X is going to be replaced by 2u raised to the power k over 2 exponential minus u 2 times du. And this is equal to, let's take this power and distribute it to both of these elements. It's going to be k over 2u k over 2 exponential minus u times, let's put another 2 here, du. All right, now note that these are constants, so they can be taken out of the integral. So 2 times 2 raised to the power k over 2 divided by 2k over 2. Hopefully these will cancel. All right, and the integral from 0 to plus infinity u k over 2 exponential minus u du. Note that these integral boundaries will not change because x is equal to 2u, so it's going to be 0 to plus infinity. And these will cancel, all right? And this is going to be equal to, note that now this exactly looks like a gamma distribution. Now alpha minus 1 is going to be equal to k over 2. So alpha is going to be equal to 1 plus k over 2. So this integral will be equal to gamma function of k over 2 plus 1. So continuing from here, we have equals, let's say 2 times gamma function k over 2 plus 1 divided by gamma function k over 2. And this is going to be equal to 2 times using the property, this property of the gamma function, right? This one here. We can write this as 2 times gamma function k over 2, gamma function of k over 2, gamma function k over 2. These will cancel, and we end up with the already found or already mentioned property of the chi-square random variable. Expected value of a chi-square random variable is equal to k. And actually now we can easily find the expected value of s square. Therefore, this is going to be equal to sigma square over k times this is k. These will cancel, and we find the result. Expected value of s square is equal to sigma square. Note that this is a less general result compared to our previous. It was another bonus video effort to show expected value of s square is equal to population variance, because this is only this proof is only confined to normal distributed x. Now, using the very same method, can we find the expected value of s here, which would mean find the expected value of that here, expected value of square root of x square, and we can call it here x. Now, the strategy that I'm going to be following is going to be very much the same, but this time I'm going to be interested in expected value of x. So these would all be cleared. And now the expected value is, note that it's a better way of showing it in this fashion. Expected value of x square square root. Show it in this fashion, because now it's easier to see the relation. Now, since x square is the variable itself, we are interested in the expected value of the square root of that random variable. So in this case, again, if you recall, expected value of gy was equal to gy fy y dy integrated over the domain of y. So here what we are going to do is, from 0 to plus infinity, we are going to be writing square root of x, and we are going to be using this chi-square random variable density function. It's going to be 1 over 2 to the k over 2 x k over 2 minus 1 exponential minus x dx. So the only thing that will change is the x in the previous operation is going to be is going to turn into square root of x. But unfortunately, that makes it actually is the part where actually bias will be formed. So let me try to continue here. Take the constants out to k over 2, right? From 0 to plus infinity here. Now this is x to the power 1 over 2. X k over 2 minus 1 plus 1 over 2, this is going to be equal to x k over 2 minus 1 over 2. So actually, we can write it that way. It's going to be x k minus 1 over 2. All right, so it's 1 over 2 plus minus 1 is going to be minus 1 over 2, so it seems correct. Exponential minus x over 2 dx. Again, the very same transformation. 2u is x and 2u du is dx. So we concentrate on this part. So it's going to be 2 to the k minus 1 over 2 x k minus 1 over 2 exponential. I'm sorry, we don't have. It's going to be u k minus 1 over 2 because 2u is x, and we have exponential minus u 2 times du. And this 2 and this coefficient will be outside of the integral. So if I put all the terms outside the integral in a nicer form, it's going to be 2 times 2 to the it's going to be 2 to the power k over 2 times 2 minus 1 over 2. All right, I have used this one here, and these two are here, which is going to be 2 k over 2 and the gamma function. Again, these terms will cancel, but note that there is an additional square root of 1 over square root of 2 here. Let's continue with the derivation. 0 to plus infinity. Here is going to be u k minus 1 over 2 exponential minus u du. And alpha minus 1 is going to be equal to k over 2 minus 1 over 2. So alpha is going to be equal to k over 2 plus 1 over 2. Therefore, this function, this integral is going to be equal to gamma function of k over 2 plus 1 over 2. And this is going to be equal to 2 times, oh, by the way, if I can, 2 times 1, this is going to be simply equal to 2 times 1 over 2. Okay, and what else do we have here? We have this whole thing, k over 2 plus 1 over 2 divided by k over 2. Now, unfortunately, these will not cancel because we cannot put this here into this form. Since we have 1 over 2 here, we cannot put it into this form here, unfortunately. Well, if you do that, it's not going to make, we are not going to be able to simplify this expression. So this is going to be equal to, and instead of this one, let's make it square root of 2 to make it even more easier to understand. This is going to be square root of x squared expectation value. Now let's find the final result, and we need to multiply by this element here, and let's do that. Then when we do that, expected value of s is going to be equal to, actually I forgot there, sigma over square root of n. Square root of, sorry, k times, so we can put into the common parentheses here, in square root we have 2 over k, gamma function, k over 2 plus 1 over 2, k over 2 times sigma. And this is going to be, as you can see, is going to be the additional factor of c here, which is going to depend on k, as you can see. So expected value of s is going to be ck. K is the degrees of freedom here, actually, which is going to be multiplied by sigma. So the bias of s is going to be equal to the expected value minus the true value here. And this ck is going to be actually smaller equal to 1. Only as k goes to infinity, we have ck to be equal to 1, and in this case bias goes to 0. This is the case. So for any k value, so for instance, let's say we have n is equal to 5, we have 5 observations sampled. We find the sample standard deviation. Then in order to determine an unbiased estimate for population standard deviation, what you do is you take this s term right here and you divide this by ck.